Let's talk a little bit about how to predict which end of a wire becomes positive as it sweeps across magnetic field lines. Now remember, this only happens if the wire is perpendicular, or at least some part perpendicular to the wire, and that it's crossing these magnetic field lines. Okay. Now it's really pretty simple. What we're going to do here is just pretend that we're a positive charge on the wire. So let's just pretend that protons can move on the wire, and let's figure out what force a proton feels. Okay. So what we do is we make our index finger be this way, right? Because that's what we do. If this was a positive particle moving through a magnetic field, we'd just make this prediction, okay? So point your index finger up the page, put your middle finger into the page, okay? And in this case, you would get that the force on this particle, the magnetic force, would be to the left, and that would make this end more positive, okay? And that's the positive, and it's as simple as that, okay? And then if you don't want to listen to my rant here, obviously that's all you really need to know. But this is kind of cool because really what's going on here is that, of course, positive particles can't move. They're in the nucleus, right? And so they're stationary. They're not going to move around on the wire. But the negative particles actually go to this end, okay? Which makes this end, of course, positive by subtraction, and there is no difference, okay? But this also means, by the way, that there's a electric field this way, an electric field in the wire, right? Okay, we know that EMF is B times L times V, right? The Boulevard equation, okay? We also know that that's like voltage, right? Okay? And if we divide voltage by the length of this wire, we get the electric field, which is kind of neat. Isn't that neat? Okay, so if I divide BLV by the length of the wire, I get that the electric field inside that wire, and we see this, this happens in other types of problems too, right? We get that there's an electric field that is equal to this. Okay, the faster you go, the bigger that electric field is. The bigger the magnetic field is, the bigger that electric field is. Okay, I guess that's the only cool thing about that. But this relates to Maxwell's laws, which we're going to learn later. This is sort of one of these universal things about the relationships between magnetic fields and electric fields. It has to do with light waves and this and that. But anyway, I'm going to stop talking. You're probably not listening right now, so